So we still have our operator region. This guy right there. That's okay. Cool. But you'll notice that we originally had this inactive repressor. But now over here it appears to be active. And how did that happen? What caused that conformational change in that protein? And the fact that tryptophan showed up. So if tryptophan is present, it acts to activate the repressor, which of course can then bind to your operator. And what does that do to RNA polymerase? Does it allow RNA polymerase to bind? So you could see here that RNA polymerase is unable to bind to the DNA. And of course this would therefore lead to having no transcription. No transcription. That means of course subsequently there would be no protein that is produced. So, yeah. Do what? Cool. So right here you're seeing with this the tryptophan operon, an operon that is usually on but can be turned off in the event that it is repressed. Cool. Blocks RNA polymerase, therefore it blocks the process of being able to cause the transcription. Good? Now let's talk about a different case real quick. Don't worry, that clock's not going anywhere. Let's talk about an operon that could be always off but turned on. So let's go back to our notes real quick. And let's jot down that there's also another type of operon. There's a different type of strategy. And that would be for an operon that would be inducible, an operon that can be turned on. So we've already talked about a repressible operon in the tryptophan. So there's a tryptophan operon. And so now let's talk about an inducible operon. Which would be like the lactose operon. And what the lactose operon is going to be coding for is this is going to be coding for a series of enzymes. And these series of enzymes will break down lactose. Now, remember, the tryptophan operon was all about making tryptophan, correct? So that was like a make operon, and this actually is coding for proteins that would be causing the breakdown of something, right? Now, when would you need the enzymes to break down lactose?
When you consume lactose.
Sensible, when you consume lactose. So only when lactose is in the media would you be needing this operon, right? So what do you think would be the agent of turning on the lactose operon, if you could guess? What? Lactose. Okay, so lactose will induce the lac operon. Of course, you could guess the lac operon is referring to lactose operon. Cool? So, I'm going to get you to draw one more little picture. Oh, yes. Guys, no tears. We've got this operon here, right? And of course, this would be the lac operon. And again, this is an operon that is basically always off, but can be turned on when lactose is present. So what we're seeing in this drawing is we're seeing basically your operator region right there. And you're seeing an enzyme right here, or protein, that actually is an inducible protein. So a protein that can be turned on, that can change its shape. Now you'll notice that this right here is essentially a repressor, if you think about it. But see, this repressor is in its active form. So again, it is in its active form. It's repressing what's in this shape, but however, it can be induced, right? It can be manipulated, and as we could expect, what would induce it? Lactose. So I'll show you the next drawing, and you don't need to copy it down. But in the next drawing, you'll see that your operator is free and clear to bind to the RNA polymerase because what's missing? The repressor. The repressor's been turned off because lactose is present. Make sense? So you've got these two kind of counter examples in operon systems. You got the type of operon that can be turned off, or the type of operon that can be turned on. This type of drawing, be ready for it on the test. Question?
So if